Now, Fred, our next story is focusing on something as messy as as what we were previously talking about, but on a smaller scale. This is stars that tend to eat their planets. It's like tigers eating their children, by the sound of things.
It's very like that, yes. Only even messier, probably, in terms of certainly what would happen to the planets that get eaten. So it's a really interesting story with all kinds of ramifications, and once again, it plays into the fortunate position that we are on our own planet, because it may be that we are relatively unusual. So
we already knew that.
We knew that, yes. But this is one of the arguments, that feeds into, for example, the Drake equation. How stable are solar systems, how long do planets last. And we live in a solar system which is extremely well behaved, if I can put it that way, in terms of the planetary motions. The planets orbit in mostly almost perfectly circular orbits. They're very stable. We do believe that in the early history of the solar system, planets migrated inwards and outwards to some extent, and maybe Uranus and Neptune swapped positions. That's something else that's a possibility. But the general picture over the last few billion years, and remember the solar system's about 4.57 billion years old, over the last few billion years, there's been a high degree of stability. And that's a great thing for living organisms to evolve. As life, for life to evolve to a high level of capability, you want it to be in a totally stable environment. And as we've mentioned many times before, one of the contributors to that might be the moon. The fact that the moon is a relatively large body compared with the size of the Earth. It's 1/80th of the mass of the Earth, which is big compared with the other moons of the solar system in relation to their parent planets. So the moon has had a stabilizing effect on the Earth's rotation, made for a stable climate, and here we are as a result of that. Highly evolved creatures from whatever origins we had. But it's possible that all solar systems aren't like that, and there is certainly among the sun-like stars in our neighbourhood of the galaxy, there are some that would be expected to have fairly chaotic orbits. Now, it's not an easy thing to detect. You can't just say, it looks as though that planet, that Jupiter-like planet, might have migrated within the last few million years. It's not the sort of thing that you can measure, because we observe these solar systems on timescales of years, not timescales of millions of years. But there is, when you look at the theory behind the way solar systems work, there is the definite possibility that chaotic orbits can have quite catastrophic consequences for planets. If you've got, planets whose orbits migrate inwards and outwards fairly rapidly, they will interact gravitationally with other planets in that system and could either kick them out of the solar system altogether, and it's possible that happened in the early days of the solar system, or sort of kick them inwards so that they are overwhelmed by the gravitational pull of their parent star and they get gobbled up by it. Essentially, they fall into the parent star, probably by spiraling inwards over many, perhaps millions of years, but eventually becoming part of the parent star itself. Now, that sort of thing is very hard to observe unless you're clever, like these astronomers who carried out this work. Once again, there's a strong Australian flavour in this, with scientists from Monash University, actually now in Italy, but doing some work on this at Monash here in Australia. What they've done is they've taken an alternative approach, which is to look at the chemical composition of the star itself. Because, and this is in a sense, it has echoes of the last story we did. If you look at the chemical composition of the star itself, you can see whether it has been polluted by elements that you would find in its planets. In other words, it changes the those elements would be in the parent star anyway, but in different proportions if it hadn't eaten up a planet. So by gobbling up a planet, you change the constituents of the atmosphere of the star. And that allows you to measure that, because we can do that with the spectroscopic technique, where you break the light into this rainbow of colors, and it reveals the barcode of information that tells us exactly what constituents are in the atmosphere of the star. If it's polluted by the debris of a planet, it will show up. And that's the really interesting aspect of this paper, because what these scientists have done is to look at there's another ingredient to the story, actually, which I've not mentioned, and that is that if you, to give you a baseline as to what your star, the chemical composition of your star would be before it ate up the planet, to give you a baseline, what you want to do is to find stars, pairs of stars in orbit around one another, things that we call binary stars, which is actually up to half the stars in our galaxy are binaries. They're two stars in orbit around one another. We're quite unusual in that we're not, or at least 50-50 we're unusual, we're not. So now the thing about binary stars is that they're made at the same time and from the same gas cloud. So they are expected to have the same mix of chemical elements.
Oh, I see where you're going.
Yeah. So if one of them's gobbled up a planet, then it will show a difference from its partner. That's the crucial point of this work. And so what these scientists...
As you love to say, Fred, that's the smoking gun.
Oh, yes, and it's probably pretty smoky if you've gobbled up a planet, yes.
Yeah, it would be.
Yeah. So what the scientists have done is they've looked at more than 100 binary systems with sun-like stars in them, and essentially looked at the spectrum of light of each of the binaries. And what they've been able to do is find how many of those stars, one star in a pair, contains more planetary material than the other one, than the companion. And the fact is that they, the stars have differences. What they found, and I might quote from this. This has been written up by one of the authors, Lorenzo Spina, in a conversation article, and he's put it very nicely. So what he says is there are three ingredients that tell you unambiguously that the chemical differences between the pair of stars were caused by eating planets. And the first is that the stars with a thinner outer layer have a higher probability of being richer in iron than their companion. This is consistent with planet eating, as when a planetary material is diluted in a thinner outer layer, it makes a bigger change to the chemical composition. Our cat's just done something a bit unusual. I'm not quite sure what it is, which is why there was a clatter there. I think he's knocked. I think all he's done is rolled over and knocked the TV remote control off where the table that he's lying on. He never lays it.
Probably investigating his new jigs. That's what's happening.
Yeah, absolutely. So I'm sorry for that digression. So thinner outer layer is one ingredient with its richness in iron. Secondly, stars richer in iron and other rocky planet elements also contain more lithium than their companions. Lithium is quickly destroyed in stars while it is conserved in planets. So an anomalously high level of lithium in a star must have arrived after the star formed, which fits in with the idea that the lithium was carried by a planet until it was eaten by the star. And then the third ingredient is stars containing more iron than their companion also contain more than similar stars in the galaxy. However, the same stars have standard abundances of carbon, which is a volatile element and for that reason is not carried by rocks. Therefore, these stars have been chemically enriched by rocks from planets or planetary material. So there you go.
There you go.
Those are the three things. And the bottom line is that between 20 and 35% of Sun-like stars eat their own planets, with the most likely figure being 27%. So, a quarter of Sun-like stars actually consume planets. They have planets that are in such unstable orbits that they dive into the star.
I'm feeling lucky. I think I should buy a lottery
ticket.
You should. Yeah. I suppose that also means that in our search for Earth-like planets, we are going to be able to dismiss 27% of scenarios because it may not be possible for these planets to exist or exist long term.
Periods, that's right.
Yeah, and that's one of the things in the search for livable planets is that they're looking for things to dismiss so they can narrow their focus.
Yes.
We talked about that some time ago.
Yep.
This may well add another element to that approach.
Exactly, it will.
So it's also a bit disappointing in that that means there are fewer Earth-like planet potentials out there because of this strange orbital situation and these hungry stars, which, I guess, you can look at it from both angles, I suppose. Of course, something else you and I spoke about not so long ago was the fact that our star used to have a binary. To be a binary, didn't it?
Probably, yeah.
We think?
I think so, because most stars seem to be formed in binary systems. So something happened, probably gravitational attraction with other stars within the same cloud of gas that the sun formed might have kicked the sibling off somewhere in the wilds of the universe, is a star which was our twin companion.
Yeah, I wonder, would it be ever possible to find it? That would be
People
a big
are certainly
ask.
looking. So what you look for is what we've just been talking about. You look for a star with an identical chemical composition to the sun, and then you try and look at its motion and sort of wind that back to see if it was ever in the same neck of the woods as the sun was. That's the way you do it.
How far apart is too far to dismiss stars being binary? I mean, what's the limit on a binary system in terms of distance between the stars?
It's measured in light years, actually. So rather millions or trillions of kilometres. And what you're looking for when you find binary stars is you're looking for stars with, first of all, this identical chemical components, but also with sort of matching velocities, so that you know that it's not just two stars that happen to be close together, that are whizzing past one another, that they've got velocities that are within cooey of each other. Yeah.
Yeah. Interestingly, though, Fred, and we've said it before, the more we start to learn about our situation, our solar system, our sun, and compare it to what's going on out there, the more we discover in terms of exoplanets and solar systems and other galaxies, the more rare we seem to be.
Yes, that's right. Indeed.
Which adds more weight to the "we are very much alone" argument.
Certainly, it certainly contributes to understanding the Fermi paradox, which is where are they all? If we're very unusual, they're out there.
Maybe so. Time will tell, but maybe not enough time for us. Who knows? This is Space Nuts. You're with Andrew Dunkley and Professor Fred Watson.
Space Nuts. You've been listening to the Space Nuts podcast.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.